Now we're going to look at determining a chemical formula from empirical data. So we identified what empirical and molecular formulas are earlier, but the empirical formula seemed a little pointless at that time. This is where we understand the significance of the empirical formula. When we have an unknown compound, we can decompose the compound into the individual elements and identify the masses of each element. From that information, we can derive the empirical formula of the compound. We can also do a slightly different experiment where we measure the masses of elements that combine to form the compound. And we're going to be doing that in an experiment in lab. We can also determine the empirical formula if we know the percent composition. So it's important to remember the empirical formula is the ratio of atoms or the ratio of moles of atoms. It is not a ratio of masses because compounds form based on individual numbers of particles. So to find an empirical formula, there are three basic steps. And the hardest part about doing these sorts of problems is just remembering what to do next. The math is really quite simple. So the first thing is we need to identify and write down the masses of each element that are present in a sample of the compound. So sometimes they'll say, well, there was 0.5372 grams of carbon, and that's great. And other times, though, they'll give you percentages. We can convert the percentage to grams by assuming that we're starting with a 100-gram sample. Because if it's 75% phosphorus, if we had a 100-gram sample, that would mean 75 grams are phosphorus. So when you're given a percentage, just divide by 100. I'm sorry, just call that the mass. The next step is to convert the mass of each element to moles. Because we can't derive a formula based on ratios of masses, just on ratios of moles. So we convert mass to moles using the molar mass for each element. And then we're going to have some numbers that are not going to be nice whole numbers. They're going to be messy decimal numbers. But you can write a pseudo formula using the numbers of moles of each element as subscripts. And then we have to make it into whole numbers. I lied. There aren't 3 steps. There's 5 steps. Once you get those messy subscripts, to get whole numbers, we identify which subscript is the smallest, and we divide all of them by the smallest. That will give us one that is 1, and the rest will be 1 or greater than 1. Now, they're probably not going to come out to beautiful whole numbers. If the result is within 0.1 of a whole number, you can round it. If it is not, like if your ratio there ends up being 1.75, you can't just round that off. Then you need to multiply. So if you understand decimal equivalence of fractions, you recognize that 0.75 is 3/4. And so if you multiply by 4, you're going to get a whole number. You can also refer to this table. The other method that works really well is trial and error. So you have a number and it's not a nice whole number, you can't round it. Try multiplying by 2. And if that doesn't work, try multiplying by 3, and then 4, and then 5. Usually you don't get past 5. So let's do an example. A sample of a compound is decomposed in the laboratory and produces 165 grams of carbon, 27.8 grams of hydrogen, and 220.2 grams of oxygen. Calculate the empirical formula of the compound. So we're given masses of the elements. What we need for the empirical formula is ratios of atoms or moles. So we're going to start with the mass of each element. So we've got 165 grams of carbon, and we've got 27.8 grams of hydrogen, and we have 220.2 grams of oxygen. we need to convert these into moles. And we do that using the molar masses from the periodic table. So for carbon, we're going to multiply by moles over grams. We find the number on the periodic table, 12.0108. So 165 divided by 12.018. This comes out to be 13.7294. We're going to end up with whole numbers, but we don't want to round off too much. We're not going to really have to consider the number of significant figures in a final answer, but the danger is throwing away significant figures. So in these problems, keep extra. It's better to have too many digits than not enough. This result would have 3 significant figures, so I want to make sure I keep some extras. So that's moles of carbon. Then I do the same thing for the hydrogen. I'm going to multiply by 1 mole and divide by the mass of the hydrogen. 1.00795. It's messy. That also should have 3 significant figures, so I'm going to write 27.5, and then I'm going to include 2 or 3 extra ones to avoid problems. For the oxygen, 1 mole, or 15.9994 grams. Again, that should, well, not 3 this time. This should have 4 sig figs. 13, sorry, 13.76. There's our sig figs, and I'm going to carry some extras. A lot of what's important about significant figures is not necessarily rounding everything exactly correctly, but understanding the idea behind it and not putting way too many or throwing some away and causing an error that way. So now we have these mole ratios. We could use these to write an empirical formula. It would be C 13.7294, H 27.5807, O 13.76302. Have you ever seen a formula like that? It's a mess. You can't have fractional parts of atoms, and so this can't possibly describe one molecule, because you can't have 13.7294 atoms. These need to be whole numbers. And the way we get them to be whole numbers is by dividing them all by the smallest number. So I look at these. I've got 13.72, 13.76. This is the smallest one. So I'm going to take all of these and divide by the smallest so that I get ratios. That is going to be exactly 1. I'm going to divide this one by 13.7294. When I do that, 27.5807 divided by 13.7294 equals 2.0089. Is that within 0.1 of a whole number? Yes, it is. Let's do this one. I'm going to divide this one by the smallest. 13.76302 divided by 17.7294. Except I punched a number in wrong. Divided by 17 instead of 13. There, that's better. This comes out to 1.0024. Can that be rounded to a whole number? Yes. So this is close enough that I can call it 1, and I can call this 2. So my formula then is C1H2O1, except we don't write the ones. So let's get rid of those. CH2O. Any questions? One molecule will have one carbon atom, 2 hydrogen atoms, and 1 oxygen atom. That is the ratio that's given by these numbers. It's just, it's hard to see them because they're such messy numbers. Any questions?
When you're
Yes.
writing it, why didn't you put the hydrogen first? Because it's on the more metal side.
Well, that's a good question. Why not put the hydrogen first? That's kind of a subtle point. We write the hydrogen first when it's an acid, and otherwise not so much.
So how would you know it's not on the end, or you know what I'm saying?
That's a good question. And I think the best thing to do when doing these empirical formula problems, use the same order that was given in the problem. I will not count it incorrect if you swap up the order. Master in chemistry might, I don't know. But if you said H2CO and showed your work, I'm like, yeah, it looks funny, but it's correct. But that's a good question. Yes?
So are all acids like the ones that have the H in the front?
Pretty much. Yeah. What happens in general chemistry is we kind of have to lie to you for your own good, right? It's like when you lie to small children. You know, where did grandma go? Well, she died, you know, but maybe they can't, you know, maybe it's their birthday the next day and you don't want to break their heart the day before their birthday, right? And so you let them enjoy their birthday and then you tell them that their beloved grandmother died. I don't know where I come up with these crazy examples. But there's some things that we kind of have to simplify and gloss over, right? The child asks, where do babies come from? You say, well, babies come from mommy's tummy. Well, it's kind of true, but then again it isn't, and we all know that, right? But it's at a level that the child can understand. And not that you guys are children, but some of these things, if I presented all the details, it would just like be completely overwhelming and pointless. So in this class, you'll hear me say that a lot. In this class, all acids start with H, and all compounds that start with H are acids. After this class, you're going to learn that there are some things that are considered acids that don't necessarily even have a hydrogen in them. It's possible. Okay? Any other questions? Let's do another one. Here's my friend ibuprofen again. Ibuprofen has the following mass percent composition. What is the empirical formula of ibuprofen? So we're going to do a very similar process here, but we're not given masses. What we do is we just take the percent sign and eliminate that and write grams instead. Because if we had a 100-gram sample, there would be 75.69 grams of carbon. And the thing about percent compositions and chemical formulas, they are intensive properties. They do not depend on the amount of substance. Ibuprofen is 75.69% carbon, whether you have a handful of it or a semi-truck full of it. The percentage is the same. So we're going to take these percentages and write them as masses. So there are 75.69 grams of carbon and 8.80 grams of hydrogen and 15.51 grams of oxygen. What do we do next? Change to moles. So we're going to use the molar masses. So 1 mole of carbon is 12. I've decided I'm just going to memorize the longer numbers. 12.0108 grams. So doing that, 75.69 divided by 12.0108. That would have 4 significant figures, so I want to make sure I write at least 4 and throw a couple extra in just for good measure. So that many moles. Then we take the grams of hydrogen and we do the same thing. 1.00 797? 796? 95. That was close. Close only counts in hand grenades and horseshoes. 8.8 divided by 1.00 795. 3 sig figs here, so I make sure that I include the 3 and then throw in some extras for good measure, because they all end up disappearing anyway. For oxygen, 1 mole is 15.9994 grams. 15.51 divided by 15.9994. And this is 0.9694. There's the 4 sig figs I have to have and a couple extras. Any questions? Individual steps are simple. It's the remembering how to put them together that tends to go out the window when you open the next exam. So we can use these to make a formula. Personally, I think this pseudo formula is stupid, but that's what the book says, and one of our labs does it too, so I better teach it to you. I think it's a waste of time. But there it is. Those are not nice whole numbers. And we can't just round them. We can't say, oh, well, it's C6, H9O1. We need to find the ratios, because the formula gives the lowest ratio of numbers of atoms of each element. So we look at our moles that we got, and we identify the smallest. Is pretty clear here. We always divide by the smallest because that gives us numbers that are 1 or larger. So this one ends up being exactly 1. And this one's going to be let's see, 8.73089 divided by 0.969411. So this one comes out to be 9.006. That's looking good. We could round that. And then let's look at this one. Divide by 0.969411. And this one comes out to be 6.501. Can I round that to 7? No. It needs to be within 0.1. So if it was 6.08, sure, you can round it to 6. If it was 6.9, I could round it to 7. But this is right in the middle. Now what we need to do is multiply all of these by the same number so that we keep the ratio relationship the same. I look at this and I say, okay, I've got a fractional part of 0.5. I know that's equal to 1/2. If I multiply this by 2, I'm going to get a whole number. And if you don't think that way, say, well, she said to start with 2. So multiply by 2, see what you get. If that doesn't work, try 3. So I still have this number in my calculator. I'm just going to multiply by 2. And I get 13.001. Can I round that to 13? Yes. Okay, this is good. We have to multiply the other numbers also. Otherwise, the ratio is going to change. So 9.006 times 3, no, 2, sorry. That's going to give us 18. And 1 times 2 is going to give us 2. So those are our coefficients. our subscripts. So it's actually C13H18O2. And that is different than what we would have gotten if we had just rounded those to whole numbers. Any questions? So that's the empirical formula. The empirical formula is helpful, but the molecular formula is the most useful. So the molecular formula will always be a multiple of the empirical formula. It could be multiplied by 1. They're the same. Or it could be 2 or 3 or 4. To find the molecular formula, we have to have the molar mass of the compound. That is not something that you can determine experimentally. That requires the use of a mass spectrometer. We're not going to learn how to do that in Chem 1A. So in solving these problems, the molar mass will be given to you. It's not something you have to calculate. It'll be given to you. The other thing you need is the empirical formula. On a nice, easy question, they'll give you the empirical formula, they'll give you the molar mass, and ask you to find the molecular formula. On a nastier problem, they'll make you do one of the calculations like we just did, and calculate the empirical formula, and then calculate the the molecular formula. So the way we solve this, we need to find what that multiplier is. You take the molar mass and you divide it by the molar mass of the empirical formula. You want to find out how many times does the empirical formula fit into the molecular formula. So here's a nice problem. A compound has the empirical formula CH and a molar mass of 78.11 grams per mole. What is its molecular formula? It could be C2H2, it could be C3H3, it could be C4H4, some multiple of CH. What we want to do is we want to figure out what the molar mass of CH is, the empirical formula. So the mass of that would be the mass of the carbon plus the mass of the hydrogen. I keep trying to use my cell phone as my calculator. It's not as effective. 12.0108 plus 1.000795. Okay, so I get 13.01875 grams per mole. So for the empirical formula, 1 mole of that formula would weigh 13.01875 grams. Everybody okay with that? We learned how to do that on Monday. I want to find out how many times this fits into 78. That involves division. I'm going to take the molecular, the true molar mass, 78.11 grams per mole. I'm going to divide it by the mass of the empirical formula. .11 divided by 13.01875. And I get 5.9998. Can I round that to 6? Yeah, that's crazy close to 6. That's 6. If you do not end up with a whole number on these problems, there's a small chance the problem could be wrong, but most likely you made a mistake somewhere. You're never going to have to multiply this to get a whole number. It should just give you a whole number. This is the number I need to multiply all the subscripts in the empirical formula by. One way to represent that is, here's the empirical formula, and I'm going to multiply everything by 6. So it's C6H6. And that's the true formula, the molecular formula of the compound. Each molecule has 6 carbons and 6 hydrogens, but CH is the lowest ratio. Any questions? It could be, it's probably benzene. Yeah, C6H6. A lot of these compounds with carbon and hydrogen can form lots of different compounds. I don't know of any off the top of my head. I don't know. There might be another one, but I don't know. How do they actually do this? How do you break something down into its elements? Well, a lot of the compounds are more complicated, but we're going to look at one group of compounds that is a little easier to do this with. And this is a combustion analysis. So you take a sample of the compound and you weigh it carefully. And then you break it down by burning it and weigh the components separately. So for organic compounds that contain carbon, hydrogen, and oxygen, this works really well. These things are flammable. You burn them, and then you collect the individual elements. So what happens is the carbon that was in the sample, when it's burned, forms carbon dioxide. The hydrogen forms water. And the original mass of oxygen is just found by difference, law of conservation of mass. I know the starting mass, I know how much carbon was in it, how much hydrogen was in it. The difference must be the oxygen. Well, how do you collect the carbon dioxide and the water? They do it like this. Bless you. So here's the furnace, and we've got oxygen flowing through here because oxygen is required for combustion. So you put the sample in there and you burn it. And all the gases that are given off as this burns flow through a series of tubes. In science, we call this a U-tube, right? And now that's funny because YouTube is a website, right, where you can watch videos about cats. Pass through this U-shaped tube. Yeah, you can watch chemistry videos too. Inside this tube is a substance that will absorb water. It'll grab all the water from this stream of gas that's flowing through and hold on to it. So we weigh this tube before and we weigh it after, and afterwards it's heavier. The difference in mass is the mass of the water that was collected. But all the carbon dioxide is going to go straight through. And it goes through to another tube where we have a CO2 absorber, and all the CO2 from that gas stream will get stuck onto this substance. And then we've just got things other than water and carbon dioxide going through and out the other end. So again, we weigh this before and after. We can get the mass of carbon dioxide that's been given off. Any questions about that? Yes?
Sorry, are they separated because of like the temperature that they separate out? Or why don't they just stop at one tube? Or
How can this just absorb the water and not the CO2? It has to do with interactions between the substance that's in here and the water. I think probably the biggest thing is that carbon dioxide is a nonpolar molecule and water is a polar molecule. And so they're going to be attracted to different things. And a lot of what science is about is making use of small differences between substances. There are a lot of things, we're always trying to separate things and identify this or that. And identifying what's different about this and what's different about that can allow you to sort things. So let's do an example here. Upon combustion, a compound containing only carbon and hydrogen, so there's no oxygen in this one, only carbon and hydrogen produce 1.60 grams of carbon dioxide and 0.819 grams of water. Find the empirical formula of the compound. We need to get moles of hydrogen and moles of carbon. That's what we're looking for. We've been given a mass of water and a mass of carbon dioxide. So the idea here, I'll write it all out with the carbon dioxide. We've got 1.60 grams of carbon dioxide. We're going to convert that to moles of carbon dioxide. And from that, we can convert to moles of carbon. The conversion factor is right inside this formula, CO2. There is one carbon atom in every molecule of CO2. There's 1 mole of carbon in every mole of CO2. And that's how we'll get moles of carbon. We'll do the same thing for the hydrogen in the water. So 1.601 grams of CO2. So we're going to convert to moles of CO2, and that's going to use the molar mass. And then we're going to convert to moles of carbon. And that's a relationship that we get from the chemical formula. This is the easy one. We look at the formula. How many carbons? 1. So there's 1 carbon in 1 CO2. We need the mass, the molar mass. So I'm going to write that down here. Got 12.01008 plus 2 times 15.9994 I'm getting 44.0096 grams per mole for the carbon dioxide. One mole of carbon dioxide, 44.0096 grams. So now we just solve that. 1.60 divided by 44.0096 times 1 over 1. That tells me there's 0. We should have at least 3 sig figs. 36356. I threw in 2 extras. Moles of carbon. Any questions? We're going to do the same thing for the water. 0.819 grams of water. We're going to convert to moles of water. And then we're going to convert to moles of hydrogen. Need the molar mass of water. 2 times the mass of the hydrogen plus 1 oxygen (18.0153 grams per mole for water. 1 mole of water, 18.053 grams of water. What numbers do I put in for moles of hydrogen to moles of H2O? 2 moles of hydrogen to 1 mole of H2O. I get that from the formula. In one of these, there are 2 hydrogens. If I was doing oxygen, it'd be 1 to 1. 0.819 divided by 18.053 times 2. I get 0.0907. Again, we need at least 3 sig figs. I'm going to carry a couple extras here. Moles of hydrogen. We could use those numbers and make a pseudo formula. Personally, don't see the point in doing that. How do we get whole numbers out of these messes? Divide by the smallest. We're looking for the lowest whole number ratio, and ratios involve dividing. So I'm going to take the smallest number, which is the one for carbon, and I'm going to divide carbon by itself. And so that one's going to come out to be exactly 1. I'm going to take this one, 0.036356. .09, 0.7328 divided by 0.036356. And this one comes out to be 2.49568. Now what do I do? Multiply by 2. I can't round this off. I'm going to multiply by 2. And when I do that, I get 4.99. So times 2, 4.991. That's close enough that I can round to 5. I also have to multiply the other ratio by 2. So I'm getting a 2 and a 5. So carbon, 2, hydrogen, 5. C2H5. Any questions? What is it? You ask hard question. C2H5. I don't know off the top of my head. I know what C2H4 is. I'm not sure that C2H5 is actually possible. Yeah, it's a relative of ethane, but I actually don't think it's a real compound. Yeah, that's kind of dumb of them. It's missing one. I should probably revise that problem. It should either be C2H6 or C2H2. I guess you could say this is a free radical there. Any other questions? Pardon me?
Ethyl radical.
Yeah, there'll be an ethyl radical. Here's another one. This one's a little more complicated. Upon combustion, a 0.8009 gram sample of a compound containing only carbon, hydrogen, and oxygen produced 1.6004 grams of carbon dioxide and 0.6551 grams of water. Find the empirical formula of the compound. This is a tedious problem, okay? It involves molar masses and some unit conversions, but it just gets tedious. And I look at this and I go, ugh, we're going to do it anyway. So here we have grams of carbon dioxide, grams of water. So we can do what we did before and calculate the moles of carbon and the moles of water. What's missing, though, is any information about the oxygen. The oxygen is found by difference. So what we have to do is we have to actually find the grams of carbon that are produced and the grams of hydrogen that are produced. And what we'll find is that those added together are smaller than the original mass. The mass of oxygen is the difference between those. The oxygen is not something that we can collect and weigh. And so this is the only way we can do it. Well, let's get started. 1.6004 grams of CO2. Well, I have to go to moles of CO2, and then I need to go to moles of carbon, and I want that answer, but then I also need the mass of carbon. So to get the mass of carbon, we're going to use the molar mass of carbon itself. Oh, I need numbers. What's the mole ratio here, moles of carbon to moles of CO2? It's 1 to 1, right? 1 carbon to 1 CO2. Molar mass of CO2 is 44.0096. We just calculated that. I just scrolled back on my calculator and there it is. This for the carbon is from the periodic table. So 1.6004 divided by 44.0096 times 1 divided by 1 times 12.0108. So the mass is 43, let's see, should have 5 significant figures. 43677. The next one's a 0. I'm going to include at least that one extra one. That is grams of carbon in the sample. I'm also going to write down the value that I would get if I stopped there. Which, if I'd been thinking, I would have just pressed equals and I wouldn't have to do this over again. But the moles, 0.03629,354 moles of carbon. We need that for the empirical formula. We need the grams of carbon so we can find the grams of oxygen. You still with me? So we found all the information we need about carbon. Now we need to do a similar process and find out what hydrogen we have. We need the moles of hydrogen for the formula, and we need the grams so we can find the information about the oxygen. So 0.6551 grams of H2O. I know it's 18.0153. Grams of water. Then I need to get to moles of hydrogen from moles of water. 2 moles of hydrogen to 1 mole of water. And then 1.00795 grams of hydrogen per mole of hydrogen. I knew that some of you are very resistant to writing your work out in this way. A problem like this is very difficult to keep track of in your head. I would have a hard time doing it, and I've been doing problems like this for longer than some of you have been alive. It's sad, but it's true. You need to be able to write stuff down so that you can remember where you're going. Because stuff happens, right? The telephone rings, or something, some idea pops into your head, you lose your train of thought, then if you don't have anything written down, you're starting over. And if you come up with the wrong answer at the end, you have no way of telling where you went wrong. When you write it all out and your answer's wrong, you can go back and look at it and find the mistake. So this time I am going to write that number down. 0.6551 divided by 18.0153 times 2. Well, I miscommunicated with my calculator. Try that again. That's better. So the moles of hydrogen, 0.72727,071 moles of hydrogen. And then when I multiply that by 1.00795, I get grams of hydrogen. And this one should have 4 sig figs. There's 73305 grams of hydrogen. Got moles of carbon, moles of hydrogen, but I still need the information about the oxygen. So I'm going to take the starting mass of the compound, 0.8009 grams, I'm going to subtract the mass of the carbon, and I'm going to subtract the mass of the hydrogen. .8009 minus 0.43677 minus 0.073305. 0.2908. This number has 4 decimal places. These all have more. This is the last significant figure, but I'm going to keep extra so I don't have rounding errors. So that's my mass of oxygen. That escaped from the apparatus, but we figure it out by identifying everything else. What do I need to do to this mass of oxygen? I need moles of oxygen. I also need more space. There's some more space. So I'm going to move up to the top. 0.290825 grams of oxygen. I'm going to use the molar mass of oxygen to calculate the number of moles. So I've got that number in my calculator. I'm going to divide by 15.9994. And I get 0.0181772 moles of oxygen. Now what do we need to do? We need to find the smallest number of moles and divide all of them by the smallest. We're trying to get whole number ratios. So I've got 0.07, I've got 0.03, and 0.01. 0.01 is the smallest. So this one ends up being 1. Those other guys are kind of hiding down there, so I'm going to bring them up here. 0.03629.354 divided by 0.0181772. So many numbers. I think I did that right. 1.997. Is that going to be rounded? We can round that one. So that one's good. Let's check the other one. 0.072727. That's an awful lot of 2s and 7s. And that comes out to 4.001. We can round that as well. So we don't need to multiply anything. So our formula then, for carbon, the number was 2. C2, H is 4, and oxygen is 1. C2H4O. Any questions? Isn't that fun?